April 7th. Okay. That's the Monday before advising day. Oops, that's the wrong one. Advising day is on Tuesday the 8th, so I want to make sure that you have all the information about class if you have an advising appointment or something along those lines. So anyway, just a reminder, we've got a few sections to cover. Obviously, since we still have a week and a half before the exam, we still have a few sections to cover before the exam. But I always want to make sure that it's in your mind that that's coming up, especially since we have some of the stuff that's going to be on the exam was before break, right? So making sure that you have think about going back and looking at that stuff before the exam on the 7th. All right. So last time we talked about exponential functions. What does the form of an exponential function look like to start with? What does it have to look like?
2x. F of x equals 2x. 2 to you.
Oh, so does it have to be a 2 though, necessarily?
No.
It could just, yeah, so it could be any number, right? So it'd be a to the x, right? That's the form of an exponential function. What has to be true about your a? There's two things that we worry about for the a. Can't be negative. Good. It has to be greater than 0. What else do we want? What do we not want it equal to? 1, right? Because remember, if it's equal to 1, we just get a constant function, right? So that's our form for an exponential function. It's some number raised to the x power. We want to make sure that that number we're using for the base isn't negative, or 0 is also not interesting either. But we don't want it to be negative because negative causes all sorts of domain issues, right? You're talking about if it would say we're -1, you couldn't do -1 to the 1/2 power and get a real number. Okay. So we want to make sure it's positive so that our domain is all real numbers. And then again, we don't want to want 1 in there either because 1 just makes a flat line, right? It makes a constant function, horizontal line. So there's a specific type of exponential function that is used in lots of different applications. We refer to it as the natural exponential function, so that's what we're going to talk about today. We'll also talk about inverses of exponential functions today as well. Start that today. But before we talk about what the natural exponential function is, what I want you to do in your calculator is figure out approximations for these numbers. Get decimal values. So what this means is for the first one, if you're just typing this in, you're going to put a 1 here and a 1 here for the first one, right? Okay. And then change it to a 10, change it to 100, 1,000, and so on, and make a table of values. If you're getting really, really, really big numbers, you've typed something in wrong, okay? So just see if you can fill out that table of those, what do I have, 7 numbers there? So hopefully you got numbers close to what I've got on here. Notice that even though what we're plugging in for n, what we're plugging in for n here is getting really, really big, and we're putting in numbers that are getting really, really big in for our exponent, are the answers getting really, really big? No. Okay. So, in particular, in general, I'll try this again. In general, for a normal exponential function, if your base was bigger than 1, what did your graph look like? If the a was greater than 1, what does your graph look like? Yeah, it goes up and to the right, doesn't it? Like that, right? So the bigger the exponents get, these numbers get really, really big for outputs, don't they? Notice this doesn't fit the form. Even though I've got something raised to the nth power, that's not an exponential function because this is not just a single constant, is it? No. Okay. All right. So notice that even though our exponents are getting really, really big, and even though all of these numbers are bigger than 1, they're getting really, really close to 1 on the inside, so it's not letting it get really, really, really large all the time. What we get is something that gets really, really close to some number. Okay? So as your n goes to infinity here, this number approaches 2.718281828 and so on. It doesn't keep repeating, actually. It looks like it starts to repeat, but then it gets different decimals as you go along. It gets really, really close to this particular number. We call this number E. Has a special name. You know how you use pi? That's a special number, right? E is also a special number. Okay. It's this number. It happens to be irrational, even though it looks like these decimals are repeating. Like I said, they change up after this point. Okay. You'll notice on your calculator, you should have a button for E. You should have a button that also says ln. The E is right above it. Yes. Yeah, it's Euler's constant. Yep, that's right. Yeah. That's exactly right. Yep. So the E stands for Euler, the mathematician Leonard Euler. Did lots of stuff in all sorts of areas of mathematics, but this is named in honor of him. All right. So the reason why we call this the natural exponential function is because of the way this number came up as a constant. What did we do? We started changing this number in here in the denominator and in the exponent. If you've done anything with financial math at all, you might recognize this as a piece of what's referred to as the compound interest formula. If you think about putting money in a bank and leaving it, and then the interest grows, and then interest grows on what it grew, and interest grows on what it grew, on what it grew, and so on along the lines. That's a piece of the compound interest formula. If you do what's referred to as continuous compounding, so rather than compounding maybe every month or every week or every day or every hour, you refer to as what's continuous compounding, you end up with this exponential function. And this is used in finance a lot, as a matter of fact. It's used in stock pricing, it's used in options pricing, all sorts of different things. Okay. So this natural exponential function pops up in business, pops up in biology, doing exponential growth or exponential, and it comes up in chemistry with the exponential decay. It's a very, very useful function. All right. So when we talk about the natural exponential function, the natural exponential function is f of x equals e to the x, where e is this 2.71828 and so on down the line. Okay? This is the natural exponential function. So e to the x is the natural exponential function. And again, you should see that button on your calculator. It should be right above what looks like an LN button. It should be in the first column, I believe. Okay. There should be an LOG, and then right below it there should be an LN. Yeah. The E should be, you have to use second to get to it. Okay. When you type that in your calculator, an E should actually pop up. Right. If you type in E to the, either with a caret or if you have it as written as E to the first power, you should see that decimal pop out. If you do E to the first power, you should see a 2.718281828. All right. So this is a number. It's a little bit less than 3. I like to joke that it's your third 3 that you know. You know the number 3. This is a little bit less than 3. What's the other number that's a little bit bigger than 3 that you know? Yeah, it's pi, right? Yeah, pi is 3.14159265358979, and so on. That's all I know, by the way. I do not want people to memorize lots of digits of pi. I get to the 8979 and I'm done. That's all I got. All right, anyway. It's a waste of brain space, in my opinion. Okay. All right, anyway. So this is kind of the third 3 that you know. If you're trying, and the reason why I mentioned that is estimation of answers is kind of an important thing to be able to do, if it makes sense. If I know that E is about 3 and I use 3 to estimate it, then I can kind of do some mental arithmetic and see if my answer makes sense. That's my calculator. Okay. So just thinking about it being about 3, if you need to check an answer at the end. All right. In any event, it's an exponential function. And the base is bigger than 1, right? So we have those properties of what it looks like. So you should already know what the graph looks like, right? When it's bigger, when the base is bigger than 1, what does the graph look like? I just drew it a minute ago. But what does it look like when the base is bigger than 1? Yeah, it goes up and to the right, right? Where does it cross the y-axis again? At 1. All of them cross at 1, right? Okay. So listing out the properties here then, domain's going to be what again? All real numbers. Our range is going to be yeah, 0 to infinity, right? We never hit the x-axis. We never go to the other side of the x-axis. You just told me a second ago that the y-intercept was 1. Is there an x-intercept? Does it ever cross the x-axis? No. Horizontal asymptote?
0.
Yeah, y equals 0. Good. And is this function increasing or is it decreasing? Increasing, right? Definitely increasing, right? So it's increasing on, whoops. If I could spell the word increasing, that would be helpful. Good. All right. Again, remember all exponential functions have these 5 same properties, right? Every single exponential function has the same domain, the same range, the same y-intercept, no x-intercept, same horizontal asymptote. The only thing that changes is does it go up or does it go down depending on what the size of the base is, right? We agree? Okay. All right. So just to give an example here, let's do another one where we do a sketching of a graph. This should look a lot like what we talked about last time. So work on this for a minute. Identify base graph, identify the transformations, and then sketch a graph. Okay? So work on that for a minute. Identify what the base graph has to be. Probably a good guess what it's going to be, considering what we're talking about for the section, right? Identify the base graph, identify the transformations, sketch a graph. While you're doing that, I'm going to hand out for the next section. This is a very, very short section, right? Sorry. We ready to chat about it? Yeah. What did you decide the base graph should be? A to the x? Good. Right? Good. We identify that as our base graph. And again, should that be going up and to the right or down and to the right? Up and to the right, right? We've got that horizontal asymptote over here. It should cross the y-axis at 1, and then it should go up rather steeply. I just missed where it should go there. Again, we're just looking for basic shape, right? We're not worried too much about exactly what points it goes through, except for I really should have made it go through 0, 1, right? That one probably would have been a nice one to do. Okay. All right, how many transformations do you see? I see 3, right? Where do you see those 3? What numbers are telling you that we see 3? The 1/2, the +1, and the +2, right? All right, there's 3 of them. We see them? Okay. All right, so let's list them out, what they mean. What does this 1/2 do? Vertical compression, good. That's a vertical compression by a factor of 1/2. Okay. It makes it 1/2 as tall, right? Does that change where your horizontal asymptote is at all? No, it's just going to make it 1/2 as tall, right? So if I draw that one in here, I'm just going to put one helping point in here to help me out. Instead of the y-intercept being at 1, where will the y-intercept now be? At 1/2, right? So I should have something that looks roughly the same, but flatter, right? Again, We're just looking for basic shape, right? We're not trying to get anything super fancy. Okay? That part okay? That's our first one. Okay? What did the +1 do? Shift to the left. Good. That's on the inside. Remember again, we talked about this last time. It's in the exponent. The exponent is the inside of the exponential function. And things on the inside affect the inputs. Right? Right? So, and then when it's on the inside and affecting the input, it kind of does the opposite of what you think, right? So since it has a +1, we're going to go left 1. I'm pointing to my left, that's your right. So left 1. We agree? Okay. All right, so instead of this point being at 0, this point should now be at -1, right? So it's really here. I'll just change the color again here. It's really here in the middle, isn't it? It's going like so. Right? I just used that one point to move it over and then drew the same graph. Okay. Last thing we see, I see the +2. What does that do? Shift it up 2 units. Now this one really does move your asymptote now, doesn't it? It sounded kind of funny. Lose your asymptote. Move your asymptote. Okay. All right. So where does the asymptote end up? Instead of being at 0, is at y = 2, right? So it'll be over here. This point now will be at 2.5, right? This point that we had right here will be at 2.5. And then again, we just make a carbon copy of our graph. It should still be relatively flat. So this one should be your final. It's not my best work as far as graphing goes, but are we okay with the process? That part okay? What questions do you have? All right. Well, this is the natural exponential function, so we're going to switch gears a little bit. We're going to come back and do more with natural exponential function. But the switching gears idea here is basically undoing these things. Okay? So we're going to talk about start logarithmic functions today, and we're going to spend more time on logarithmic functions on Friday as well. We're just going to get our introduction in here, what we're talking about. So remember, we have those two basic shapes for our exponential function graphs, right? Either, I'll just draw them back over here on this side. Either it goes up and to the right, or it goes down and to the right, right? We agree? This is your exponential function where your base is greater than 1. This is your exponential function if your base is between 0 and 1. Those are basic shapes, right? It's one of those two, right? And really, it's the same shape. This is just this one flipped, right? Flip left to right. We agree with that? Okay. In any event, those are your basic shapes. But what do we notice? If I look at the graph and take horizontal lines, how many times do those horizontal lines cross? Just once, right? Remember that was our test for being 1 to 1. So that was our horizontal line test. And what did we use that for? If it passed the horizontal line test, if it was 1 to 1, what could we find? What other function could we find if it was 1 to 1? Started with an I. Inverse, right? We can find an inverse. So every exponential function has an inverse function. Okay? That's the goal for this section. Since exponential functions are one-to-one, and that's why we make sure we define them the way we do, right? We want to make sure the domain is everything. That's not necessarily important for inverse functions, but we don't want that flat line that's not one-to-one. Okay. All right. So since it's one-to-one, it has an inverse. We're going to define what the inverse function is, and that's what we refer to as a logarithmic function. So the definition is, the notation is y equals log with a little a subscripted here and an x. Okay. We read this as log base a of x. That's how we read it. Okay. All right, so this is what we mean by the logarithmic function. Now I need to define it in terms of the inverse, okay? So remember, this is supposed to be the inverse of the exponential. Remember, inverses reverse the roles of x and y, right? Inputs become outputs, outputs become inputs, okay? So if I think about flipping that around, my exponential function would be a to a power, but I need to flip around my x and y. Okay? So the input here is now the output for the exponential. The output here is the input for the exponential, right? That's what inverses do. They reverse the roles of x and y, right? Remember when you solve for inverse functions, the first thing you did was flip-flop your x and y? Right? Same idea. The important part is to recognize where these things are. This output for the logarithmic function corresponds to what? The exponent, right? That's all logarithms are. Logarithms are exponents. That's all they are. They sound super mysterious. There's a weird name that goes along with it, right? But literally, a logarithm is just an exponent. Okay? That's all it is. Right. So let's see if we can practice this a little bit and rewrite what we refer to as exponential equations into an equivalent logarithmic one. All right? So let's look at this first one. In particular, let's look at the left-hand side of the equation and ignore the equals 81. If I want to think about that as an exponential function to start with, what would be the base of your exponential function be? Well, just the number is all I'm asking for, sorry. Yeah, just the 3, right? The base is 3, isn't it? What's been plugged in for x? 4, right? That's my base. That's my exponent, right? Okay. So when I write the logarithmic equation, the base goes here, right? This is the base of the exponential. That's the base of your logarithm, okay? I'm just going to write it in the same form that I have up above, but you can flip-flop it. We said the 4 was in the exponent. Is that the input for the exponential? For thinking back to the exponential function, is the 4 an input or is the 4 an output for the exponential? Input, right? Because it's in the exponent, right? The exponents are the inputs. What happens when you do the inverse? Inputs become outputs, right? So this should be on the equal sign, right? Okay. Okay. Over here, now let's look at the right-hand side. Is that for the exponential function, does that 81 represent an input or an output? Output, right? Okay. Outputs for the original become inputs for the inverse. Okay. Now, usually we would write it the other way around and just write the equals 4 on the other side, but it doesn't really matter. Okay? But just notice where the parts are. Base, exponent. Exponent is the output, right? And then output, input, then for the end log. Okay? Now, if we want to think about what this question is really asking you, it's asking you what power, when I see a logarithm, remember outputs for logs are exponents, right? What power on 3 gives me 81? Okay, I'm looking for an exponent. What exponent on 3 gives me 81? Or 3 to what power is 81? Okay, and it happens to be 4. That's good. Right? What's that? Okay. Yes. This is the input for the exponential. It's the output for the log. And it flips right. Yeah. All right. So notice the next one doesn't quite look like the previous one, does it? It's a little bit different. But I've got this radical here. Can you convert the radical into an exponent? How would I rewrite that? 125 to what power? 1/3. Good. Remember that when you have a fraction as an exponent, the denominator tells you what root to take, right? So since it's a cube root, it's a 1/3 power. If it were a 4th root, it would be a 1/4 power, and so on up the line. Okay. All right, so when I do my log, what are you going to use for the base? The 125, because that's the thing that's the base in the exponential part, right? Okay. What are you going to use for the input for the log function? The 5. Remember, the input for the log is the output for the exponential. What are you going to use for the output of the log function? The 1/3, because that's the input for the exponential or the exponent, right? This part right here is always the exponent. Okay? Always the exponent. The thing that's on the equal sign opposite the logarithm, that's always the exponent. Okay? Does that make sense? Okay. So you tell me how to write the next one. Yeah.
C equals log base B of Q.
Good. Okay. So again, let's go through the different pieces. Why is the B here? That's the base of the exponential, right? Okay. Why is the Q here? Because it was the output, now it's the input, right? Why is the Z here? Oops. That's because it's the exponent, right? Logarithms are exponents, right? So the exponent's always going to be on the opposite side. Does that make sense?
Always only the exponent?
Yeah, it's always only the exponent. Yep. Okay. All right. This one wants us to go the other way. This one wants us to start with a logarithmic equation and end up with an exponential equation.
What if the exponent is equating itself?
Oh, that's okay. It could be an expression. Yeah. We'll see. We'll see equations. We'll see equations that we'll solve where the exponent will be an expression. Yeah. We'll deal with it. Don't get too far ahead. Let's just practice this right now. All right. I want to convert this to an exponential equation. Right? So remember, these are what we refer to as the exponential equations in the previous example, right? Okay. Looking at this first one, what base do you think you want to use for your exponential? 7. Good. Oops. Let's go back to black here. 7. What exponent do you want to put on 7? 2. Good. Because that was the exponent there, right? Okay. And what does that have to equal? 49. Good. So again, notice the form that we have here. Okay. Notice the form. Base, base, right? Those two are what matches for those different things. Do you agree? Okay. The output, remember, output for log is an exponent. So that's what goes in the exponent, right? And then input for log is output for the exponential. That makes sense? Rewriting these around? All right, let's do the next one. What's the base? 1/9. What's the exponent?
Negative 3 halves.
-3/2, and the output must be 27. Cool. Put the parentheses. Just making sure that I make sure you apply the exponent to both the top and the bottom. Because if I don't put the parentheses, then it just looks like the -3/2 might be on the 1. So that's why I put the parentheses around it. So you tell me the next one.
Base is B. Exponent is M. Product is W.
Yeah, e to the m power equals W. Yeah. BMW. Buy a BMW, be prepared to pay a lot for maintenance. Whew. You have to go to special stores to go get them, to special dealerships to go get them work done and all that stuff. So nice cars, but expensive ones to own. Well, and buy, but also own. And they got to do insurance and all that good stuff. This okay? Okay. Let's talk about what the graphs look like. Get the properties down, and then we'll do more examples next time with these things. All right, so remember how we got graphs of inverse functions back when we talked about them, right? So we're going to have two different graphs depending on the base again, okay? So let's say your base is greater than 1. What does your exponential function look like if your base is greater than 1? Goes up and to the right, right? So I'm going to draw that one first. This is going to be our helping graph to start with, right? Okay. So our exponential function goes up and to the right this way, right? When you graph inverse functions, remember we flip-flop x's and y's, right? So we do that reflection about the line y equals x. Right? Okay. We flip-flop x's and y's. So let's think about a couple of pieces of what the graph has to look like and then draw it. Okay. First, what are the coordinates of this point right here that I'm pointing at? 0, 1, right? We're going to flip-flop x and y to get the graph of the inverse function. So instead of the point 0, 1, we're going to have the point 1, 0, right? So on your inverse function, we'll have the point 1, 0. Okay? Does that make sense? Flipping the x's and the y's? Okay? Now let's think about the exponential function again. What do we have right here? A horizontal asymptote, right? What's the equation of that asymptote? Y equals 0, right? Inverse is flip-flop x's and y's. So instead of the equation y equals 0 for an asymptote, if we flip-flop x's and y's, what do we get? X equals 0. What kind of a line is that? A vertical line. Good. So for your log function, you're going to have a vertical asymptote. Okay? The horizontal asymptote changes to a vertical one. And now I can draw my graph. Again, it should be a mirror image. So it'll go up and to the right like this, but more slowly. So this is your, I guess I should have drawn it in red, but that's okay. This is your inverse function. I'll write it as a g of x equals log base A of x. Still going up and to the right. We cross the x-axis at 1 rather than crossing the y-axis at 1. We've got a vertical asymptote of x equal to 0 rather than a horizontal asymptote of y equal to 0. Flip-flopping the x's and y's. That's what it looks like if your base is bigger than 1. Doing for the other graph, between 0 and 1, what does your exponential function look like if it's between 0 and 1? Down and to the right, so it'll go this way. Again, your y-intercept becomes what? It becomes an x-intercept, right? Your horizontal asymptote becomes a vertical asymptote. And again, we're going to reflect about the line y equals x, which is that line right there, right? And now this one looks a little bit different. I am going to draw this one in red just so that we can see it a little bit better. This one's going to come down this way and go that way. So this is going to be your log base A of x. Remember, what did we say looked like the relationship between the graph of when the base is bigger than 1 and base is between 0 and 1? What did we say the graphs were? They were flipped this way, weren't they? Left to right. What does it look like for the log function? It's flipped up down, right? That makes sense, right? Because what do inverses do again? We flip-flop x's and y's, right? So instead of flipping left, right, we flip up down to get the two different graphs. Okay? So this are your two basic shapes for your log function. So let's see if we can write down what the properties are, and then like I said, we'll play with more of these next time. Again, inverses reverse x and y. Change inputs to outputs, change outputs to inputs. Okay? For logarithmic functions, your domain of the log corresponds to the range of the exponential, right? What was the range of any exponential function? That's the domain. So the range is going to be 0 to infinity, right? So that's going to be our domain for our log function. And notice that's what we see on the graph, isn't it? It doesn't go to the left of the y-axis at all. Okay? What about your range for the log function? That should be the domain of the exponential, which is going to be negative infinity to infinity. And again, we see that on the graph. The x-intercept now is, it was 1, 0, right? Is there now a y-intercept? No. Where did we see that vertical asymptote? X equals 0. And then what tells you the difference between increasing and decreasing? It goes up and to the right if the A is greater than 1, and it goes down to the right if A is between 0 and 1. Okay. All right. We're going to play more with logarithms, and we'll do more interplay between exponentials and logarithms over the course of the next week. Okay. Have a good one. I'll see you on Friday, if not before.